of different workloads. You may have heard of the term spec CPU workloads. These are workloads or benchmarks, a set of benchmarks that are designed to exercise the processor itself, CPU itself. They're not intensive in terms of I/O operations, for example. They don't do a lot of disk accesses, but they exercise the processor. There are also other benchmarks like spec web workloads. These are intended to be representative of some of the web workloads, like e-commerce applications. You set them up, you run your system, and you figure out how much time it takes, or how many transactions can your system sustain in a given second. And there are other ones, I think, Java workloads, like JVB. I don't remember what JVB exactly stands for, but these are intended to measure Java workload performance. And these are standard benchmark suites. So just to give you an idea of what's in the spec CPU benchmarks, there are two different categories, floating point and integer. And these are essentially floating point intensive applications. They exercise floating point units a lot. These are usually scientific applications. For example, there's one of the benchmarks I like is SWIM. It's shallow water image modeling. So it models images on the water, if you will. It's a scientific application. There's an earthquake simulation application called eQuake. So these are used to, you take these applications, you compile them, and you run them on the processor, figure out the execution time, and you run them on another processor, figure out the execution time, and these are meant to serve the purpose of comparison between those two different systems. Does that make sense? So, of course, let's say you design a processor X, and you designed there's another processor Y from your competitor. Let's say processor X does really well on this benchmark suite that contains, let's say, all of these applications. The processor X does great. Processor, let's say, on average, it takes, 10 seconds per benchmark. Here, this processor takes 20 seconds. Of course, that doesn't mean that this will hold true for other benchmarks, right? So, for the web workloads, processor X may take, maybe 1,000 transactions per second. I'm making up numbers here. Whereas processor Y may take 10 transactions per second. Okay. So this is benchmark set 1 and benchmark set 2. So if you look at these two different sets, the processors perform very differently. So which processor would you pick, right, in that case? It's really, performance is something that's workload dependent, if you will. So you would pick your processor depending on which workload you care about. Okay. So the way these processors are designed, you almost always design your processor for workloads. And how specific you get determines how special purpose your processor is, right? You guys know about special purpose versus general purpose processors? The idea of special purpose processors is you design your processor, or even the entire system, if you will, for a given application. Let's say eQuake, earthquake simulation, figuring out how the earthquake propagates. That's the only application you care about. You can optimize your processor to execute that much faster, right? Perhaps that application does a lot of floating point adds and multiplies together. Maybe you generate an instruction that actually does that for you, right? Just for that particular application. That's special purpose, basically. In the extreme case, one workload optimized for one application. Okay. General purpose, designed for many applications. So you would like good performance on many applications. Of course, there's a trade-off here, right? If you specialize your system for a given application, you'll get the best performance potentially on that application, right? On that application you specialize for. Whereas if you run that application on the general purpose system, you probably won't get as good performance because this system was not designed for that application. But this system was designed for many applications. Which means that now if you run some other application on this system, you'll probably get worse performance. So that's the idea. With special purpose, you get good performance on one application. And if that's the only application you care about, that's great. But you don't get good performance on other applications. With general purpose, you get good average performance on many applications, but you don't get the best performance, best possible performance on any application, if you will. That's the trade-off. And a lot of things we discuss in this class are actually have been general purpose so far, but the techniques are applicable to design a special purpose processor. Okay? You could imagine customizing your pipeline for an application's characteristics. Okay? And we can talk about that. So how did we get to this? You mentioned that you tested your application, you tested your processor or design on the suite that we gave you. You can get very good performance on that suite, but then we have another suite to test your designs, right? You may not get very good performance on those designs. So how do you get good performance on those designs? You generate your own suite, if you will. And I mean, almost always, when you design your processor, you evaluate your design across a set of workloads. Of course, you cannot have all of the workloads in the world, right? Otherwise, your design will take for a long time to do. In fact, you're designing a processor today, and that's going to be running applications 10 years from now. How do you know which workload it'll run? Remember the first lecture? I think in the first lecture we discussed that you don't know the future. You don't know what applications you'll run. So you do your best based on the current workload set you have. And as you increase the workload set you have, and you want to get better average performance across a different set of workloads, the more general purpose your processor becomes. And the key thing in a general purpose processor design is really getting the best average performance as well as getting as good as possible performance on each workload. And that makes it general purpose processor design hard. In a sense, this is easier because you know your application. As long as you know your application, you can customize your design. In fact, you can, if you know your application, and if you can generate hardware just to do the work, you can map your application directly to hardware, right? Maybe you don't need to really translate it to instructions. Because think about it. If you think about it, instructions are more of something that's from the general purpose domain, because you have a layer, if you will. You have the application, and remember the transformation layers. We have the ISA, and we have the logic. These instructions enable some general purposeness, if you will, because all applications can use these common set of instructions to be mapped to logic, and the logic implements that. Whereas if you want to be very special purpose, why do you really need that? You can take your application and assuming you can generate logic that exactly does what your application needs, then you don't need that translation layer. You don't need that inefficiency, if you will. Because instruction execution has its own inefficiency. Remember, what is that inefficiency? You need to fetch the instruction. You need to decode the instruction. You need to figure out its operands. And whereas here, for example, if you could map your entire application to the logic, like a data flow graph, for example, if you could generate that data flow graph and map it onto the logic and configure the logic to do that, you eliminate that inefficiency. Does that make sense? So some existing hardware actually supports this. For example, field programmable gate arrays. These are essentially reconfigurable logic where you can configure it based on the application's requirements. And that could be a better special purpose design. We will not cover this in this course, but you've seen that probably, right, in your earlier courses. So you could generate special purpose designs with this. But even more, these are still configurable, right? This is still provides some configurability, except at the logic level, not at the ISA level. you can have an application-specific integrated circuit that's even more special purpose. That way you directly map your application to a logic that's hardwired for that application, assuming you can do that, of course, because your application may be much bigger than what your hardware can anticipate, if you will. Okay? So I don't know how I got diverted to this, but your testing of your design with the benchmarks we provide, it's a good thing to do, of course, but I would encourage you to test your designs with other benchmarks that you write on your own, because that way you can optimize your design, especially if you're doing extra credits. That's a very good thing to do. But even for functionality as well, because the tests we provide to you are not comprehensive. Okay. Well, with that note, I think we covered this. So you know that there's a lab due on April 23rd. And get started. Debugging the lab will probably take more time than actually doing the lab. Okay. Yes? Okay, no questions. Good. So last lecture we started on memory latency reduction and tolerance techniques. And we covered, remember, full window stalls. We covered 4 fundamental techniques to tolerate memory latency. You guys remember what those were? Multi-threading is one. What else? Caching. There you go. Out-of-order execution. Prefetching. Yes. 4. That's great. And these are actually 4 techniques that have been worked on for a long time. And we're going to cover more of prefetching today. We covered a lot on software and hardware prefetching and prefetcher throttling. So today we'll do more prefetching and we'll do rented execution, hopefully, if we get to it. These are your readings. I haven't decided which one should be your required reading. But I would encourage you to read both. These will cover some of the issues on prefetching that we finished at the end. And yeah, well, this will probably be assigned reading, but I haven't picked it fully yet. But these will both be on the website, so you can look at them. Okay, let's go over these, what we were talking about, just to warm you up. This is not the best place here for me. I'll just move here. So what were we talking about? There are 2 major approaches to actually tolerate the stall or reduce the stall due to memory. One is actually trying to eliminate the stall. Right? Prefetching tries to do that. By prefetching data, you don't need to stall anymore if you prefetch it early enough. Or once you stall, how do you tolerate the effect of that stall? Right? Let's say you couldn't eliminate the stall. How do you tolerate its effect? And prefetching and caching try to reduce or eliminate stalls. On the other hand, multi-threading and out-of-order execution kind of try to tolerate. When you get a stall, you can tolerate them. Although out-of-order execution, you can argue that it also does prefetching, if you will, right, by looking ahead a little bit. So the line gets blurry. And these are the 4 techniques that we talked about. So let's go to prefetching. We talked about 4 key questions on prefetching. What address to prefetch, when to initiate that prefetch, where to place the prefetch data, and how to actually do the prefetching in general. Like, does the software do it, hardware do it, they do it cooperatively somehow, or is there a separate thread that you execute to do it, which is essentially cooperative. And hopefully you know the trade-offs related to when and where. We'll cover more of what and how today. And this is a how, just to warm you up again. Software prefetching ISA provides prefetch instructions, and programmer or compiler use those instructions to decide what to prefetch and when to prefetch. And where to prefetch as well, because remember the prefetch instructions that were provided in the x86 ISA? Based on the instruction opcode, the data would go into L1 cache or L2 cache or L3 cache. Of course, just as an aside, prefetch instructions do not provide correctness, do not require correctness, right, as we discussed. So it turns out the specification of the prefetch instruction over time can change. Because the designer, for the designer, the most important thing is, processor designer, the most important thing is to get the processor correct. A prefetch instruction affects only performance but not correctness, which means that if the design's time to market, you're running into the deadline. And the idea is you have to finish your design, and you have to get it correct. And let's say you haven't implemented prefetch instruction correctly. You prefetch instruction says this prefetch T0, I think. That says prefetch the data into the L1 cache. But the designer ran out of time. They couldn't get that correct. They may decide to prefetch the data into L2 cache, right? They may decide to drop the prefetch instruction. Well, in a sense, this is a soft contract between the hardware and software. Because prefetch there is no guarantee that's provided by the prefetch instruction, as you saw in the prefetch not the handout, but from the Intel manual. So in fact, what happens in real designs is, let's say, remember we saw buffers in the memory system. Let's say you have a memory request buffer, and you issue a prefetch from a core, and it turns out the memory request buffer is full. What do? Prefetch instruction doesn't require correctness. Most designs, they drop the prefetches. So you haven't fully obeyed the specification, if you will. But you don't have to, in a sense, because it doesn't require correctness. It doesn't affect your correctness. So what you will find in a lot of these designs is, if the hardware design becomes, if you have, for these instructions that are prefetch instructions, usually the hardware designer does not make his or her life complicated, if you will. They try to take advantage of the fact that these don't require correctness, and in corner cases, they drop the prefetches. Does that make sense? Okay. Hardware prefetching, on the other hand, hardware in this case tries to figure out what to prefetch, when to prefetch, and where to prefetch again. Basically, it does so by monitoring processor accesses and figuring out patterns or strides. So this way, the software is not aware of the hardware prefetch. Now, you could imagine more cooperative ways of doing that. Let's say you have a hardware prefetcher that tries to detect strides, and the software can tell it the stride will be this. Right? Then the hardware prefetcher can make it, the hardware's prefetcher's life could be easier, if you will. You could imagine designs like that. And there have been processors that have been implemented in such a way. And execution-based prefetchers will cover this a lot today. Basically, you execute a thread that is prefetching data for the main program, separately from the main program. And again, this could be generated by either software, programmer, or hardware, and we'll see all of the approaches. Okay, so in the last lecture, we've covered how to design hardware prefetchers for regular patterns. Stride, how to detect strides in hardware. And stream prefetcher was a special case of stride prefetcher, if you will, where your stride is 1. Except you may not need to detect strides in a stream prefetcher. You can just assume that you're just streaming through memory. And that was the stream prefetcher design we discussed. So that's very simple to implement, if you will. Potentially a more interesting and difficult question is, what about more irregular access patterns? What if you don't have a stride? What if, for example, you have a linked list that the processor is traversing through, and these are the nodes, if you will, and the addresses have pretty much nothing to do with each other. They're all over the memory. There is no stride here. How can you prefetch something like this? And there are a bunch of other patterns like this. I'm not going to go into all of them, but you could imagine like indirect array accesses or multiple regular strides. How do you detect this? It turns out this is a little bit easier than the linked data structures or random patterns. And you actually prefetch random patterns. You have no idea what the address, what next address, or what next n addresses are going to be. How can you prefetch them? Well, just the fact that a pattern is random means that it's not predictable, right? So pattern detection will not work in that case. So you have to do something else, if you will. So let's take a look at some of these. I'll cover 3 things: correlation-based prefetchers, content-directed prefetchers, and pre-computation or execution-based prefetchers. And if you have something random, if you will, you will need to do something like this. You'll need to basically maybe execute the program ahead and figure out, compute those addresses ahead. Because those addresses are not detectable by pattern. But if you execute the program, or if you are able to execute a piece of the program, you can figure out those addresses, right? Compute those addresses. Okay, so let's take this example. You're prefetching, the processor is accessing a linked list. And let's say the processor is accessing that linked list over and over again. Let's say you have only 4 elements in your linked list. And what happens is, what the processor does is A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. This is actually very prefetchable, right? You know exactly, after you see A, you'll see B. After you see B, you'll see C. After you see C, you'll see D. After you see D, you'll see A. Looking at 100% prefetch accuracy, except for the first part, you learn where you learn. So this is the idea of a correlation, or correlated address-based prefetchers. Correlation-based prefetching. You correlate the previous address you've seen with the next address you have seen. And you record this in a table. And the idea is, let's say you have a table. You can think of this as a key value store, if you will, or next address store. You index the table with address A, and when you see address A, let's say you record address A. This is the current address, and the next address, B. Let's say the processor accesses address B. What it does is it indexes here and records the next address that's seen when it sees the next address, C. And then the processor sees address C, the next address is D, and then D, the next address is A. Now next time you see A, you index the table or search the table. You could design this in many ways, right? It could be like a cache structure. It doesn't need to be fully associative, and you know all of those basics now. The purpose will not be caching. The purpose is actually designing the table. When you see, when the processor next time generates the address A, it indexes into this correlation table, if you will. That's what's called correlation table. And it sees that, oh, the last time I've seen address A, the next address was B. So I'm going to issue a prefetch for address B. And then when the processor sees address B accessed, or missed in the cache, it again indexes into this table. Oh, the last time I've seen address B accessed, the next address was C. So I'm going to issue a prefetch for C. And so on. In fact, so one problem with this is, what if the distance between the addresses, the time you access address A and address B were very small? Then your timeliness is low. It's too late to prefetch B when you see address A. Does that make sense? Because the processor is going to access address B 5 cycles after you access address A. So how can you improve this? Well, one way to improve this is actually, when you see address A, prefetch BCD. And that'll work in this case, I think. Does that make sense? Or another way is potentially you change your key, right? You look at address AB, and when you see address AB in sequence, then prefetch CD. So it doesn't work very well in this case because we have only 4 addresses. But if you extend this to 1 million addresses, let's say A, B, C, D, E, F, G, H, Y, well, I guess I cannot go through the alphabet very well, but you get my point. Basically, when you access address A, you can prefetch n accesses, n next accesses you've seen in the past after you access address A. What does this mean? This means that you correlate address A with a couple of next addresses. Instead of next address, you have next addresses, if you will. when you see address A, you prefetch B, C, D, because you record it. That was what you see. Okay? That's the idea of a correlation prefetching. And, well, more generally, it's really based on this. It's also called Markov prefetching. Because it's really based on this graph. Things may not be as nice as this, right? So here, in this case, whenever we see address A, the next address is B. But it may not always be like that, right? Sometimes, when you see address A, the next address could be, I don't know, X. And as you execute your program, maybe with 50% probability the next address is address A, address B, with 50% probability the next address is address X. Why could this happen? Well, you could take a branch, for example. Or it could be that this is not a linked list. Okay? It could be that you actually have a tree, for example. Right? And sometimes you traverse the left part of the tree, and sometimes you traverse the right part of the tree. So the pattern you see is really dependent on where you go, depending on the branch. Okay. So if you look at the processor's access tree, and these could be misses. So these are all cache misses from the L1 cache, let's say. Or these could be processor accesses. That goes back to at what level you place the prefetcher, right? Does it see all of the requests from the processor? Does it get placed in the L2 cache, L1 cache, L3 cache, memory controller? Basically, this is the access pattern that prefetcher sees. So if you look at that access pattern, you could construct a graph like this, where the nodes of the graph is an address you see, and the arcs on the graph specify the next address you see after this address, and the numbers on the graph specify the probability that you would see that next address after, given that you've seen that previous address. That's the idea of this Markov model. You form this model, and you could construct this dynamically, potentially. But let's assume that we've seen all of these, and we've constructed this. In this case, this graph hopefully corresponds to this access pattern over here. Well, you can verify that, I guess. Let's try to verify that. Like, according to this, after you see address A, with 60% probability, you'll see address B. With 20% probability, you'll see address A again. And with, oh, that's the wrong direction. And with the remaining, I guess here, 20% probability, you'll see address C. So how do you compute this? If you look at address A, the next time, once you see B, once you see C, once you see A, another time you see B, another time you see B. So there are 5 times A appears, and three of those times you see B after A. And once you see C after A, and once you see A after A. So 3 divided by 5 is 60%. So at least that part of the graph is correct. So you could go through this. For example, between B and C, there's perfect correlation, if you will. Once you see B, always the next address that's going to be referenced is going to be C. And if you look at this, that's true. BC, BC, BC. So the processor can dynamically construct this graph. And based on this, when it sees A, let's say, likely it issues a prefetch for B. Or it could be, you could say, oh, I've seen A, and the likely blocks after this are B, C, and A again. Of course, you don't issue a prefetch for A, but you issue a prefetch for B and C. So that's the idea of Markov prefetching. And this is what I've kind of shown you, right? You construct this table. You can think of this as a key value store, where the key is the current address you've seen, and the value, if you will, is the next address. And basically, you record the likely next addresses after seeing an address A. And next time A is accessed, you prefetch those recorded likely next addresses. And A is said to be correlated with BCD. That's why it's called correlation for prefetching. And the correlation could be high or low, depending on this probability, if you will. It could be that, let's say you've seen A 1,000,000 times, and every time it was a different address after A that came. Well, then that's probably you don't want to prefetch in that case, right? That's the purpose of the confidence counters here. Confidence means how many times after you saw this address you actually saw this prefetch candidate address, if you will. And you can increment those counters. Okay? So it's hopefully a simple concept. And it works really well for this kind of case, right? For a linked list. So there are some downsides, of course, with every idea. Well, prefetch accuracy is usually low, especially if your probabilities are low. Which means that usually what happens is you have multiple prefetch candidates, which are essentially after A, what came after A, and with what probability, and you try to prefetch all of them at the same time. Now this is bad, of course, right, because you'll see probably only one. Well, you don't know exactly. Maybe you'll see the other address later on sometime, but this, now you're increasing your coverage, if you will, coverage of misses, but you're reducing the accuracy, because you're generating more prefetch candidates, but probably only one will be useful. Okay. So you can actually increase coverage. You can also, how do you improve accuracy? Well, instead of correlating with one previous address, this is what I was mentioning before, you might want to wait. Like you might want to change the key such that your key is not only a single address, but multiple addresses. Meaning, if you've seen A and B consecutively, then you prefetch C. And you could extend this, right? You could say, you have to see 3 consecutive addresses, and based on that, you record the next address. Let's say, how do you do that? Let's say you've seen A, and you've seen B, and almost always the next address is C. Well, what you want to do is ABC. And somehow record this, hash this as a key into your store. Okay, that improves your accuracy because remember what's happening is really you're not looking at one address to correlate with the next one, but multiple previous addresses, if you will, to correlate with the next address. Does that make sense? Okay, good. So this is, if you're more interested, this is described in this seminal paper, Prefetching Using Markov Predictors, ISCA 97. Actually, there were earlier papers from Cornell that also describe the idea, but this explains things a little bit more clearly. So what are the advantages? Anybody? That's exactly. Yeah. Can cover actually kind of arbitrary access patterns as long as you have this kind of predictability. Linked data structures, especially a linked list that does not change a lot, is very prefetchable. How about streaming patterns? Can you actually prefetch those? Let's say you have A plus 4, A plus 8, A plus 16, dot, dot, dot. Exactly. Well, if you come back, you can prefetch these. Except it's not very efficient, right? What happens to your table if you do this? Well, you have A plus 4, A plus 4, A plus 8, right? Because that's what you see after you see A plus 4. And then A plus 8, A plus 12. And then A plus 12, the next thing you see is A plus 16. A plus 16, okay, I can go on forever, I guess. A plus 20, but you get the point, right? This table can quickly become huge, especially if your array, if you will, let's say it's 1,000,000 entries. You have a 1,000,000 entry table. That's horrible, right? The stream prefetcher can capture this much more efficiently because it just detects the stride. The stride prefetcher. It just detects the stride. Storage is much less. Whereas here you're going to store all of these addresses. And that directly goes into the disadvantage of this approach. This correlation table needs to be very large. Imagine, again, even for a linked list, let's say your linked list never gets modified. If your linked list is, I don't know, maybe 100 entries, it's okay. You'll have a 100 entry table here. But let's say you have a huge database, and you, for some reason, programmed it as programmed to access it as a linked list, and you have a billion entries. Well, you don't want to have a billion entry hardware table in your processor, and that's the biggest downside of this approach. And that's why it's actually not used in a lot of processors, even though it's a nice idea. At least like this, the way it's proposed, it's not used in processors. Because recording every misaddress and its subsequent misaddresses is infeasible. It works for small problem sizes, small sizes of data structures, but in real world, you don't see those small sizes that much. And anyway, yes?
Why don't you restrict the size of the table and then use eviction?
Yes, you could do that, but then by the time you come back, you evicted everything, right? So once you, let's say your table size is 10, and you really traverse through 100 of these, by the time you come back, it's all gone from the table. Of course, you could decide not to evict after some point, and by the time you come back, you'll prefetch only this part. So that could work. But then that requires sophisticated policies to detect actually what you should evict and what you should not evict. Okay? So timeless is limited, and we talked about this, because a prefetch for the next access and miss is initiated right after the previous, and you could solve this problem by prefetching more, like future accesses that you see, but then that reduces your accuracy. So that, again, it's the classic trade-off. If you want to improve your timeless, you've got to be more aggressive, but that reduces your accuracy, and that also increases your intensity in terms of bandwidth. It consumes a lot of memory bandwidth, especially when these probabilities, correlations are low. Unless you employ confidence. But once you start employing confidence, then you're not generating prefetches. So your coverage goes down also. So one disadvantage of this is it cannot reduce compulsory misses. Remember, one nice side of prefetching was we could reduce compulsory misses. We could prefetch an address that we've never seen. But here, is that the case? Well, you have to see the address first, right, to form the correlations between addresses. Okay. So how else can we prefetch these linked data structures? Actually, the accuracy and timeless linked lists are a nice case if they fit in the correlation table. But what if you have a binary tree, right? Now your correlations become harder. What if you have an n-ary or k-ary tree? And once the data structure becomes dynamic, once you start sorting, this approach doesn't work. So what else can you do if you want to prefetch for these pointer-based data structures? I'll give you another idea. It's actually a clever idea, I think. This content prefetching is a specialized prefetcher to prefetch pointer values. And the idea is, when we bring a cache block into the processor, why don't we look at this cache block and figure out what are the addresses in these cache blocks? If there's an address in that block, let's generate a prefetch for that address. The anticipation is that you brought this cache block, which contains some pointers, and you're going to access those pointers soon. That's the idea. Well, the advantage is now you don't need to memorize or record past addresses, right? You wrote a cache block, you scan it, figure out what's a pointer, and you may have never seen that pointer and never touched that pointer before. And you can generate the address. And it can eliminate compulsory misses. Well, I guess I've given you this one. It can eliminate compulsory misses. But there's another advantage. You don't need to record the past addresses, because the address is in the cache block itself that you brought into the processor. So this is essentially a stateless mechanism. It's very cheap. The downside of this is it really indiscriminately prefetches all pointers in a cache block unless you do something intelligent. So what if your cache block contains many pointers, okay, and you're going to touch only one? In a sense, there is no confidence mechanism in this case. Yes?
So how can you possibly know something's a pointer if
Yes, we're going to get to that. That's an excellent question. How do you know what's a pointer? Right? You just get some values in your cache, right? How do you distinguish what's a pointer and what's not?
That'd be really interesting because, like, if there's something in your cache block that looks like a pointer but isn't, that does that create like a page fault? You can access it.
Yeah, but again, you don't need to be correct in this case. So what you do is you drop the prefetch. So you take a virtual address from your you take a value from your cache block, treat it as a virtual address, access the TLB, and the TLB says this is a page fault, or this. In the end, you figure out that it's a page fault, and you don't handle that page fault. Right? In fact, for prefetches, page faults are not handled because if you handle them, well, I guess you could handle them necessarily, but then you'll need to handle them speculatively.
Yeah, it seems like that could reduce the utility of this stuff because it has to be in the TLB, and that means you have to have access to that page before.
That's right, and that's one of the implementation issues that we didn't get into in prefetching, but I'll encourage you to think about those. There are all these. So if you do the prefetching based on virtual addresses, yes, you will need to somehow figure out is that virtual address, what is the physical address corresponding to it. If you do the prefetching based on physical addresses, then you're still limited by what happens if you go across a page boundary. You may actually be prefetching for some virtual address that you're never going to touch. Okay? So I'd encourage you to think about those issues. Those are interesting issues, but we don't have a whole lot of time to go into those. Yes?
So do you only prefetch pointers from a cache block that you have already touched? Or
No.
Let's say you use that to get an address and then you fetch that cache block and that has many more but you never touched it. So and that has another.
Oh, I see. So you're saying multiple levels. Yeah. So what he's asking is, you got a cache block, you found a pointer in it, and you prefetch the cache block pointed to by that pointer, and that prefetch cache block has other pointers. We actually prefetch those pointers, and that's a design choice.
You could potentially be basing lots.
That's right, exactly. So, but you could improve your time limits in that case, right? You're prefetching much farther ahead. So you can read this paper. There's analysis in that paper in terms of what you do. But let's get back to the question of how do you identify a pointer? Any guesses? Well, one thing is software can tell you. Software can mark the pointers. And that's easy. The software knows what's a pointer, right? Assuming you specify it in that's what you declare in C, right? Yes?
Or can't the memory just be arbitrary data? So like whatever format you use to identify a pointer, then you can also use that.
That's right. Yes, that's right. It doesn't always work. If you have a strongly typed system, then that works. But sometimes you can C, for example, you can use anything as a pointer. You can cast anything into a pointer. But that could be a possibility, right? The software can have specify what's a pointer. But let's assume that you don't have that software information. Can you guess, if you will, what is a pointer?
You can check your permission bits.
Check your permission bits.
To see
How would that work?
To see if, like, within the scope of the program, if you're actually, if that address is accessible, and it might not be an address, but it's possibly.
Or just looking at TLB.
Okay, well, but they don't, yeah, I guess you could do that. What is a simpler way? So you have, let's say, a 64-byte cache block, and you have 4-byte values, let's say you have 4-byte addresses. Is that true? No, that doesn't make sense, right? Yeah, 4 bytes, yeah, 32 bits. Which means that you have 16 values in your cache block. The question is, how do you determine whether a value is a pointer? And there's actually a clever way of doing this, at least approximating it. And the idea is, you have an address for the cache block, right? And if you will, this is a 32-bit value. So in a sense, you know that if you're within the vicinity of that address, it's likely a pointer. Does that make sense? So if the top bits of this address of the cache block is the same as the top bits of a 4-byte value within the cache, and you declare that 4-byte value to be a pointer. Is that reasonable? Because this is an address. It's likely that something that has the top bits the same will be an address too. It may not be. It may be a value. But it turns out it is more likely an address. And that's the idea. Compare address size values, if you will, within the cache block with the cache block's address. And if most significant few bits match, then declare that it's a pointer. Just to give you an animation of it, let's see what's happening here. Let's say we're fetching this cache block with this address from DL2. Well, I guess it needs to go into DRAM first, not go back into DL2. And you bring the cache block into DL2, and these are the values you see, if you will. Well, ignore those values. Basically, you have comparators that take the top, in this case, 12 bits of the cache block address and compare it to all of the 4-byte values and the top 12 bits of all of the 4-byte values within your cache block. And here, one of them matches, and you generate a prefetch for it. So it turns out this happens to be close to this address. And this doesn't match, but maybe it's a pointer, right? You don't know, so you may miss some of the pointers in your cache display. Okay? But if your linked nodes, if you will, are allocated close by, it's likely that you would like to prefetch something that's close by, rather than that's far away. Okay, make sense? So the problem with this is it's really that you may have many pointers here, right? And you'll prefetch all of them. So you could make this more efficient, and I'm not going to get more into a whole lot of detail here. And usually efficiency comes from getting more information from some higher level. And hardware basically doesn't have enough information on pointers. You could design the software such that it communicates what's actually a pointer. That way you're sure what's a pointer, except for cases where you don't know exactly what's a pointer, when the software doesn't know exactly what could be a pointer. And software also can get information about how the pointers are used. Okay. So the idea in more efficient content prefetching is have the compiler profile the code and provide hints as to which pointers are used in a cache line, which pointers are more likely to more useful to prefetch. And the hardware uses that hint to prefetch only likely useful pointers. So with a load instruction, you get a hint saying, for the cache block this load instruction brought, prefetch these pointers. Why could this work? Let me give you a specific example. This is actually a hash table lookup. And you traverse through this linked list that has a key and pointer to 2 data structures and a pointer to the next node, if you will, in the linked list. And this is how a cache block is organized in this case, right? You have a pointer to the key, which has pointers to the 2 data structures you touch. Actually, this is a real program that computes the minimum spanning tree. And then this is the linked list. Oh, this is actually the hash table. This is the hash table. You have buckets, and each bucket you have a linked list. So what happens in this traversal is when you look up a key, you get into a bucket, and then you traverse the list, right? Which means that you touch all of these pointers. But you touch the data pointers, you need to dereference those pointers, only if the key matches. So what's the likelihood of the processor actually touching the key pointers versus the data pointers? These are much more likely to be actually accessed. Okay. Whereas these are unlikely to be accessed. Because only if your key matches. And if your linked list is long, the probability of your key matching is low. Which means that if you have information about this high-level structure, then you can have the content directory prefetching only these pointers and not these. But at the hardware level, you have no information about this. You could perhaps potentially reverse engineer, but the logic you design for that could be very complex. Whereas the whole purpose of content directory prefetching is stateless prefetching. Yes?
although in this case you won't be accessing many keys either because it's going to set vault. Whereas it's going to set the node to the node next and then easy reference it regardless of whether it's null.
Okay, so you don't like my program here. All right, without checking it, I see. Okay, anyway, you could write your program in a nicer way, perhaps. Check it. But that's the idea. Okay. Assuming your program works correctly, you could provide information from the software. And this is exactly right, because this is your node, and this is how your linked list would be laid out in your cache line. You have the key, data 1 pointer, data 2 pointer, next pointer, key, data 1 pointer, data 2 pointer, next pointer. So this is one node, this is the next node. And if you bring this cache line, if you prefetch all of these, you'll be prefetching 1, 2, 3, 4, 5, 6, 7, 8 pointers, assuming all of them match with the virtual address. But if the software tells you that this key is much more likely to be accessed, you just prefetch those 2 keys and not the other pointers. Okay? And I'll just go through this. Okay. Any questions on this? Okay. So let's move on to other kinds of prefetchers. So we would like to cover more patterns, as many patterns as possible. This content prefetching is an interesting idea, but it works for only linked data structures. Right? What about even more general accesses that where you don't even know whether you're accessing pointers or something? You just get cache misses, right, for some reason. These are hardest to cover, of course, hardest to figure out. You have to somehow figure out what the address is. And execution-based prefetchers were developed to actually make these, prefetch these addresses that are very difficult to identify otherwise. And the idea is simple. You execute a piece of the program concurrently while your main program is executing and generate the addresses earlier than your main program will generate. That's the idea. Basically, pre-execute a piece of the pruned program, if you will, solely for prefetching data. You really need to execute the piece of the program that actually leads to the cache miss, right? So if you can somehow identify that slice of your program that leads to the address computation correctly, then that could be a much smaller program. So you could make this prefetch program very small, if you will. And this is also called a speculative thread. This pre-executed program piece can be considered a thread, if you will. And it can be executed in different places. It could be executed on a separate processor, core, if you have another one. While you're executing the main program in this core, the main program can say, spawn this thread that will prefetch for me in this other core. It could be on a separate hardware thread context. If you have a multi-threaded processor, one thread could be executing the main program, the other thread, the other hardware context could be executing this prefetch program, the speculative thread. Or, as we will see, it could be on the same thread context in idle cycles. Let's say this main program stalled because it got a cache miss. Now you could switch in this speculative program to do the prefetching while the main program is stalled. And we'll see a method of doing this. Yes?
So will this speculative program also generate cache misses?
Yes, that's right. But hopefully those are cache misses that the main program will get to. Hopefully those are not separate from the cache. So you actually, that's a good point. When you construct your speculative program, you better not be adding new cache misses.
So
but it's really the same address space, so it's a thread. So hopefully it's not going to touch spurious places. We'll see an example of it.
So basically you're just anticipating the cache misses in advance and then...
Exactly. That's the idea. Okay. So how do you construct the speculative threads? You can prune the program and insert spawn instructions in software. Or you could do it in hardware. I'm not going to do the hardware method. I'll show you some ways of how to do this in software. Because hardware, well, at least the pruning part. Or you could use the original program to do the prefetching, but execute it faster. And we'll see a way of doing that. Remember, the idea of the speculative thread is it's speculative. anything it does is not going to be committed to the architectural state. That's the definition of speculation. Okay? So it could ignore some things in the program and keep executing just to get to those cache misses. Okay. The idea of this speculative thread, it needs to discover misses before the main program, otherwise there is no point in executing it, which means that you need to compute less somehow to get ahead of the main program, or you need to avoid waiting or stalling. To get ahead, you should use something like this. Like you can perform only address generation computation. And it needs to, what if you don't know a value, right, that goes into the speculative thread? Well, you can do value to it. So let's take a look at it pictorially. So this is the idea pictorially. This is your main program. Ignore this branch for now. I'll get to it right after I describe the load. But you could do this for branches also. And I think one of you suggested last time when we discussed this partially that you could do this for branches. The idea is you have these fork points in your main program. And you can fork a thread at some point here. Let's assume that we have a load instruction that you figured out frequently misses. You could construct a slice that leads to that load instruction that computes the address of the load and take that out as a speculative thread. Basically here the abstraction is you have instructions that lead to the computation of the address of the load. And you package that as a thread, and somebody, let's say the compiler or the programmer, inserts a point in the main program that says fork this speculative thread that's going to prefetch data for this load instruction. And when the main program gets to that fork point, it starts executing the speculative thread in parallel with the main thread. And while the main thread is executing, the speculative thread executes, and in the end, it generates a cache miss, hopefully to the address that this load is going to reference. And that cache miss is handled while this main thread is executing other instructions here. And when the main thread gets to this load instruction, now that load instruction hits in the cache. Yes?
So are you forking off to run later parts of your process?
Exactly, in a sense, yes. Later parts, but you don't need all of the things that you do here in the main program for the load. You need some of the things, so you can actually figure out what those things are and package them as a small thread. Yes?
That sounds like incredibly costly, though, to work out another thread. You probably need a system call to do that, right?
Yeah, so if you have hardware support, it becomes much less costly. If you actually have instructions that fork, that copy your, so let's say you have a multi-threaded processor. If you have an instruction that says fork your context at this point, and this is not visible, let's say, to the operating system. You don't need to go to the operating system to actually generate a new thread. Then you could do this. But yeah, if it's a very heavyweight process, so this is a thread. It's not a heavyweight process. It's a thread that shares the same context, if you will, the same memory space with the main program. But you're right. It really depends on at what level this fork gets exposed. Okay, and we'll see some examples. Okay, so that's the idea. So you could do this potentially for a branch as well, right? Let's say you have a very hard to predict branch. And it's the same idea, right? You cannot design a branch predictor that can detect that can improve the prediction accuracy for this branch. Well, if you actually do the computation of that branch early, you could use that as a prediction. And that's the idea here. For this heavily mispredicted branch, you form a thread which essentially does the computation that's needed for the branch. And there's other stuff in the program that does other things that is not needed for the branch. So you take those out and you keep the things that actually affect the branch's outcome. And you fork that thread early enough such that the computation that's needed for the branch is done by the time the branch is fetched, and you need to have some hardware support to communicate that result to the branch. And when you fetch the branch, you say, oh, this thread already executed, pre-computed, if you will, the outcome of that branch, so I'm going to use that as a prediction. Does that make sense? Yeah. So you could do this perfectly, if you will, but you may not be able to do this perfectly also. Right? What if, at this point, this thread needs some register values, but they're not available necessarily, right? Because you're pruning the program. So you could predict those values. That's why this is actually a prediction. It's not an exact result. Also, there may be other branches that are taken in the meantime, right? The path you follow here is not necessarily the same as the path you follow here because you pruned the program. Okay? So you can actually read some of these. These are all good papers. This explains how to do the branch prediction. This explains how to do both loads and branches, and I'll give you some examples from this. So there are issues in this, of course. Basically, where to execute the pre-computation thread is one. We've kind of talked about this. And you could do this on a separate core. If you do it on a separate core, now the threads don't contend with each other, right? Which means that the main thread can run undisturbed. Right? If you execute the pre-computation thread, now you're on the same core, but there's more contention. So, actually, let me give you just an example, because it's a trade-off again, because it's not black and white. So we have, let's say, core 0, core 1, and when you send the pre-computation thread here, first of all, it takes longer to send it to another core, to spawn it in another core. But now this thread can run without disturbing the main program. And if these cores somehow share caches, the thread can prefetch into the shared cache. We haven't talked about this, but you can imagine cores sharing caches. You could have multiple thread contexts, thread 0 and speculative thread, if you will, in the same core. And if you execute these, the speculative thread on the same core, now spawning is fast. The downside is these two threads execute at the same time, right? Remember, fine-grained multi-threading, let's say. Now your throughput for the main thread goes down because you're sharing resources. But the upside is now you're sharing via one cache, right, at that level. So your prefetches are much closer to the core. Or you could do it on the same core, same context. Like you don't have an additional context. That's the cheapest way, if you will. You have one context. But when this context is stalled, you switch to this speculative thread. Now it's not as nice, if you will, because when you get to the fork, you cannot fork it right away. You have to wait until the main thread stalls. So you can think about the different trade-offs here. But hopefully we'll see a nice way of doing this when the main thread is stalled, without even requiring a pre-computation thread. Okay, when to spawn the pre-computation thread? Well, obviously you need to insert these spawn instructions well before the problem loads, right? How far ahead? Again, it's the same trade-off. If you insert that spawn instruction too early, you do all this speculative computation in the speculative threads, but you may not need it because there's a branch that took you, and you never execute that load that you pre-computed for. Or you never executed for it in the same way that you would have executed the main program. If you're too late, then again, if you're too late, what would happen is this thread would generate the cache miss maybe here, right? And by the program came to that load and you're too late. The prefetch was useless. All that pre-execution was useless, if you will. Or you could do it when the main thread is stalled. And we'll get to that. So when you terminate the pre-computation thread, so if you're, do you terminate it here, for example, when it gets a cache miss, do you terminate it? Or do you keep going after the cache miss? Maybe you do more iterations, right? More. Or maybe you figure out that this thread is too late. Do you terminate it if you can figure that out? Because let's say you're already too late, you already reached the load, maybe you would like to cancel that thread. So people have proposed inserting cancel instructions or based on feedback. So there's a good paper that discusses this. You should take a look at it. And it actually has results on real simultaneous multi-threading processors. We briefly discussed it. Right? They develop methods of forking these threads on another thread context based with this approach. You fork the speculative thread on another thread context to prefetch for the main program. And for example, where do you gain benefit? Let's say you're traversing through multiple pointer chains. Think of this like a hash table that we kind of looked at. Okay? You go into a bucket, you traverse through this pointer chain, and then the next iteration you go into another bucket and another pointer chain, another bucket, another pointer chain. So while you're doing this linked list traversal, you could potentially execute threads that do these traversals. Okay. Does that make sense? That way, you can overlap the latency of the two traversals. By the time by the time the main program actually gets to the second linked list traversal, all of this data is prefetched into the cache. And by the time the main program gets to this third traversal, all of that data is prefetched into the cache. Yes?
Why would you be looking through multiple chains? And then if it's a cache table, then it's a partition. So if you're given element, you should only search one chain.
But let's say you have many inputs, right? You have a big input coming into multiple inputs that you search for in your hash table, and you do it in a sequential manner. Okay? So there are other ways of doing this. I will not discuss this, but you can look at it. Or another thing could be your program is a bunch of function calls, right? Foo, bar, bass. I don't know what this is. I've seen foo, bar before, but I haven't seen these before. But anyway, while you're executing this function call, you could actually spawn a thread that executes the next function call. And that thread would prefetch the data that's touched by this function call, and by the time the processor gets to that function call, hopefully all of that data will be prefetched. And when the processor gets to it, well, you have it. Or you could spawn a thread on potentially perhaps branches. Let's say this is your program. You could spawn a thread that prefetches this side of the branch. And at some point you may get to it. Oh. Okay. Well. This is for you to read. But this is just an example. This is an example similar to this multiple pointer chains, and this is from the Spec 2000 benchmark, MCF, if you will. This MCF does some vehicle scheduling. So what it does is it has this, lists, multiple lists that it traverses, and I guess the lists are actually trips, different trips to schedule the vehicles, if you will. And each iteration of this for loop traverses a different list. If you look at this, you get the pointer to the beginning of the list, and you do this traversal to figure out, I don't know, something. And the next iteration, you get the pointer to the next list and do the traversal. And the next iteration, you get the pointer to the next list, so on. So what you could do is, while you're doing the traversal of this list, you could spawn a thread that does a traversal for the next list. And that's what this does. And you can read this in your own time. I just copied it from the paper to make it helpful for you. But what could happen is, at this point, you could have a pre-execute start instruction that spawns the next iteration to another core. And while this main program, if you will, is traversing this list, this next program, the speculative threads can be traversing the next list. That's the idea. And you could look at the code on your own to see, here's the start. Oh, where does it start from? So when you start the traversal of the current list, if you will, what does this pre-execute start do? It says start pre-executing the program from this end 4, which means after this list. So end 4 is when the traversal of the current list is done. So here, in a sense, we're not even pruning the program. We're just saying, before you start the traversal of this current list, why don't you also spawn a thread that does the traversal starting from N4? And N4 is essentially the next iteration. Right? You start from the end of the traversal of the current list. And nothing is incorrect here, hopefully, because you also check all of those counts, right? You check the loop index counts. So basically, this pre-execution thread essentially executes the next iteration. And there's a pre-execute stop here, if you will. You execute only the next iteration. When the pre-execution thread gets to this pre-execute stop, it says, okay, I'm done. And by the time it has traversed through the entire list. Okay? So the paper also proposed some ISA extensions. The paper evaluates these with real system. So this is the question you asked, I think. There is some overhead in terms of actually implementing this pre-execute start in real systems today if you don't have good support. So what the paper does is the paper it proposes some extensions to the ISA, instruction set architecture, which are actually evaluated in many processors. This is a very powerful concept. The idea is pre-execute start. You have an instruction that requests an idle thread context, and it's executed only by the main thread. And stop essentially stops the thread. It's an instruction again, and you can cancel the execution of the thread. Then you can read this. And these are low latency instructions rather than going through system calls, as you potentially suggest. So what is the benefit of this? I'm not going to go through this in detail, but this is the normalized execution time over a baseline. And I think this is the baseline on the left, and PX is the pre-execution threads that are, I think, manually generated in this case. And for many applications, the performance improves. So reduced execution time reduces. And you can read the paper for more analysis. For some applications, actually, execution time actually increases because of the overhead of this execution. So you always have trade-offs here also. Yes?
Is it one major disadvantage of an approach where you run it on 2 cores that now you're using another core that you could have used for another real thread?
That's right. Absolutely.
Because
So this is not doing it on different cores. This is doing it on a different thread context. But again, same argument applies, right? You could use that thread context for something else. That's true. That's another way of tolerating latency. And if you're okay with it, perhaps that's a better way of tolerating latency. But it's not clear, right? Now, do you care about this thread's performance, or do you care about overall throughput of all threads, or of all main threads in your program, or of different applications, if you will? It really is a design choice in that case. And you could make it configurable also, right? If this is the only thread that's running in your machine, or if the user somehow specifies that this is the most important thread, maybe it's better to use that core to do speculative execution like this, instead of using it for some other application that the user doesn't necessarily care about. Again, I'll go back to my wires checker example. Do you execute your wires checker in this core, or do you actually execute, I don't know what people use these days, something that's, you're compiling code. You guys compile code, so you're a very loud compiler. Do you want it to run faster by executing a speculative thread here? Okay. So these results are actually without pruning the program, and these are on real systems. So if you could prune the program, you could actually do even better. And I'll go through this very fast. But the idea of pruning the program is here you have some problem instructions that they've identified. It turns out that this pointer access misses in the cache a lot, and this branch condition is hard to predict. So what they want to do is actually construct a thread, if you will, that has the minimum number of instructions to generate the address for this cache miss and to generate the computation of the condition for this branch. And I just like to show you how much you can eliminate. You can see that this is a big program, and this is the translation of it into the assembly code. I don't know if you can see. I cannot see this very well. Do you guys see this? Okay, so this load instruction is the problem load, if you will. It misses a lot. And this branch instruction is the problem branch. It gets mispredicted a lot. And there's some fork point that they've decided somewhere here, I think. Yes, somewhere here. And all of these instructions, if you want to construct a thread that prefetches the load and also computes the condition of the branch, these are the only instructions that you actually need. So you don't need all of these instructions because they do something else in the program. Right? And something else is, if you care, you can figure out what that something else is, which is the other part of the program that maybe some other loads that don't miss. Right? So your pre-computation thread, if you look, can be relatively small, depending on your program, of course. In this case, I don't know, they don't have the number of instructions, but you can count 1, 2, 3, 4, 5, 6, 7 instructions. Right? Whereas here you have, I don't know, at the ballpark, maybe 18. You can verify my prediction of 18. Okay, make sense? So this could be a powerful concept, especially if the compiler can reduce that to code. And this is based on the compiler reducing the code. Okay. Any questions in pre-execution based prefetching? Is it interesting? No comment? You could actually try it on your machine. Okay. So one of the downsides of these pre-execution based methods is they're relatively complex. Somehow they need to involve the software, right? And if you want to do this, then they need to involve the software even more. Can we have some, and they need a thread context, a separate thread context, right? Unless you do it when the program stalls. So I'll tell you about a method that has a simple pre-execution method for prefetching purposes. And the idea is, when the main program stalls, you keep executing the main program just to do prefetching. That's the idea of run-ahead execution. Let me show you, well, I guess this doesn't work too well. I'll do this, because I have other slides. I'll motivate another way also for you. The idea is when the main thread stalls, why don't you keep pre-executing instructions? Why could this be good? Let's get back to this 8-entry instruction window example that I gave you previously. Do you guys remember this? Ideally, you would like your instruction window to be very large, right? Such that your main program doesn't stall. But instruction window size is limited, and you cannot bring in a new instruction into the window and execute it because you don't have space. But if you had brought in this new instruction into the window, it may generate a cache miss. And now you can execute that cache miss in parallel. But you cannot do that. And you've seen that altumists are responsible for many stalls. Now, what happens, what I didn't show you before, was what happens with a large window. What if you increase the size of your window to, in this case, I think, 16 times larger, 2048 entry window. And it turns out you can improve performance significantly. Your altumis stall fraction goes down significantly. Now you may have a question on the slide, so I'll pause a little bit. If you don't, I'll move on.
Why doesn't non-stall compute time increase?
There you go, exactly. Why does the non-stall compute time increase? You tell me. It's
because now you have to have more. It takes longer to look up because you have to look up the miss buffer.
Yeah. So instead of stalling, now you're actually computing. Right? But you may be computing useless things because you have a branch predictor, and you may have mispredicted, right? If you want to build a very large window, and if you want your compute time doesn't change. So this is not the useful compute time, if you will. This is the time when the processor is not stalled at all. And by converting stalls to computation cycles, you're increasing the computation cycles. If this was a useful compute time, then that shouldn't change, at least not significantly. Okay, so we would like to get the benefits of this large window, if you will, but without paying the cost of it. But then we've already figured out that building this large instruction window is a challenging task, right? You remember why, right? We covered it in multiple lectures, actually. Basically, the problem is out-of-order execution requires large windows to tolerate today's main memory latencies, and main memory latency increases, now you need even larger window. But you cannot build this window because it's hard to build it. If you increase a large window, you increase the tag matching logic, you increase the load store buffer, which is essentially a content-associative search also. Okay. We discussed that. That increases your energy consumption, that increases your access time to the structures, and that also makes the design very complex. So we don't want any of this. We would like to get the benefit of a large window with a smaller window, or in a simpler way. In fact, the scaling of window size is a major issue in making auto-mode execution more efficient. So how do we do this? Well, one of the benefits of a large window is really memory level parallelism, right? It's really to tolerate latency. You need a large window usually when you stall for a long latency. And why do you stall for a long latency? When you get a cache miss. And how does an out-of-order processor enable memory level parallelism? It overlaps the latency of different independent misses. So if you realize that, maybe we would like to design a processor with a small window, but that can, when it gets to a cache miss, it can capture this memory level parallelism that would have been captured with a large window. Does this make sense? Well, we've already seen many ways of doing it. So that's the idea of run-rate execution. Instead of building this very large window, you get the small window, and when you get to a cache miss, what you do is, when the oldest instruction is a long latency cache miss, the processor checkpoints the architectural state and enters a special mode. What does checkpointing architectural state mean? It checkpoints the register file, essentially, and the program count, so that you can get back to it. And the special mode, called run-ahead mode, is purely speculative pre-execution mode. Just like a thread that we've seen, speculative thread. Except you're actually executing the program itself. And the purpose is to just generate prefetches, just to figure out, just to compute addresses and actually bring them into the cache if they're cache misses. And the key is, if you have, well, you stalled because an instruction was an L2 miss. Then what do you do with that register, right? You don't know the value of that register. Well, you mark that register as invalid, that you don't know the value. And if an instruction touches an invalid register, too bad, you drop that instruction. You cannot execute that instruction. Right? That way you can bring in new instructions into the window. That's the idea. And when the original miss returns, this instruction that caused entry into this speculative execution mode, when it comes back, you record that somewhere. Then you restore the checkpoint. The processor restores the checkpoint, the program counter, and the register file state when that miss happened, and starts re-executing instructions. So that's the idea. And you can, maybe we'll assign this paper so that you can read it. So if you look at it pictorially, ideally what we want is this, right? You want compute, you get loads, and they all hit in the caches. But what we get today is these small windows. You get a load 1 miss. For a while, the processor continues computing and decoding instructions, but once the window gets full, the processor stalls. Can you guys see that stall? Or is it just me? There's a stall over there, by the way. I think we have, this is supposed to be very black. I think we're having issues with the projector again. And after some point, that miss comes back. Now the processor can continue computation. But then it encounters another load miss. After a while, it stalls because the instruction window gets full. And once that miss finishes, it continues computation. And this is a very typical timeline you see in many memory-intensive applications today. That's why the processor stalls for 50 to 70% of its time, because this latency is very long. So the idea of run-ahead is, when you get to this miss, and when that miss becomes the oldest instruction in the window, now you know that you have a good state there. Checkpoint the architectural state instead of stalling, and go into the speculative mode where you speculatively execute the program, taking out instructions from your window when they execute, or if they're invalid. This way, while this miss is being handled, you can keep executing the program speculatively, and hopefully you'll get to that load 2. And if load 2 is actually independent of load 1, you could generate the cache miss, and that miss, you can start handling it with the first miss. And when the original miss comes back, the processor flushes its pipeline, so there's some penalty, that should be ready. And it restores the checkpoint. The checkpoint says, oh, your program counter was load 1. So the first instruction executes as load 1. And now load 1 hits in the cache, because you just handled the miss. And the processor keeps computing. At some point, miss 2 gets handled. And when the processor gets to load 2, that miss 2 hopefully is already in the cache. And now you've saved a bunch of cycles. You saved a bunch of cycles because instead of stalling, you pre-executed the program and generated this miss to be handled in parallel with the original miss that would have otherwise caused you to stall. Instead, you did some speculation instead of stalling. That's the idea. So you could view this as a prefetcher. That's where the line gets blurry in terms of tolerating or reducing latency. Right? You're actually using this small instruction window to do prefetching. Right? You're prefetching for future loads in your program. So this is a speculative thread, if you will. Right? Except you didn't construct it. You were using the main program for that purpose. Does that make sense? Okay. So what are the benefits? Instead of stalling, pre-executed loads and stores that are independent of the L2 miss instructions generate very accurate data prefetches. Okay. These are very accurate because you're actually following the path the program would have followed anyway. You're not trying to detect a pattern. So you can actually generate prefetches for both regular and irregular access patterns. You can get to the next iteration that does a traversal. Also, you could do instruction prefetching this way. Instructions that are on the predicted program path are prefetched. And if you have a hardware prefetcher, you can actually train that hardware prefetcher by going ahead, right, instead of stalling. So there are multiple benefits. So that's the idea. Let's cover this in a little bit more detail. So I told you that you enter run-ahead mode by checkpointing the architectural register state. But how does instruction processing happen in run-ahead mode? Simple, actually. It's the same as normal instruction processing, except it's purely speculative, just like a speculative thread. And you know what that means by now very well. And L2 miss dependent instructions, and this could be L3 miss also, depending on when you go into run-ahead mode. They're identified and treated specially. They're quickly removed from the instruction window. Right? Their results are not trusted. And how do you do that? Because basically there are two types of results that are produced, invalid and valid. Invalid means dependent on L2 miss. So when you get a load instruction, that loads a value to register 2, let's say. This got a cache miss, and this became the oldest instruction. Now R2, you have in your register file bits saying whether each register is valid or invalid. Right? Now R2 is marked invalid when you enter run-ahead mode. Another instruction, let's say, comes and sources R2, adds sources R2 and writes the results into R3. In which case it reads the invalid bit. One of the sources is invalid, which means that the destination will be invalid, so R3 will also be invalid. So all of these invalid bits get propagated through the data flow of the machine, or an out-of-order execution machine. Yes?
And then at the end, just the ones that are invalid, you go back and replace them? Or?
No, invalid, you don't do anything with these. Because these values, you're in a speculative mode. You know that these values are not to be trusted. You don't know these values. So you don't use these values. Which means that when you get an instruction like add, you just say, I cannot execute this instruction. So when it becomes the oldest instruction in the window, I'm just going to throw it out. Yes?
So you said you don't update architecturally visible state, so memory. So what happens if I have a store and then a load?
Yes, we'll get to it. That's a good question, very good question. Okay, so these are marked invalid in the register file and also the store buffer. I'm not going to get into that. But the idea is not to use these for prefetching or branch resolution. Right? Let's say you predicted a branch during the speculative execution, and it turned out that it's sourcing an invalid value to compute its direction. Well, do you trust your branch predictor, or do you trust its invalid value? Actually, that's a design choice also when you design the processor like this. But we did not use it when we designed it. So the idea is you don't trust the value because the value is stale. Okay. So how do you remove the instructions from the window? Basically, oldest instruction. When instruction becomes the oldest, you have a decision to make. Do you remove this instruction from the window, from the machine, or do you keep it for a while? Well, if an instruction is invalid, you remove it immediately because you're not going to execute it. If an instruction is valid, now you can actually execute it, and you wait until it completes execution. Right? That's how you actually generate the prefetches. Because there are some valid instructions, valid loads that compute addresses that miss in the cache. So we call this pseudo-retirement, for lack of a better term, but it's really not retirement, because retirement, by definition, says you're going to update the architectural state. So this allows the processing of later instructions. So when you pseudo-retire an instruction, which means move it out of the machine, they free all of their allocated resources, right? They should. And that way you can bring in new instructions to the machine that you couldn't have otherwise brought in. And this kind of addresses potentially your concern. What happens if you have a store in memory? You're not going to update the architectural statement because it's purely speculative. But there may be a later load that needs that value. And if you want to do accurate prefetching, maybe you would like to communicate that value to the load. Actually, you don't need to. Right? One thing you could do is, if you have a store, you can just not update anything. You can just ignore the store. Why? Because this is purely speculative. There's no requirement on correctness. Does that make sense? Exactly. It can affect the accuracy of your prefetching, and that's why actually when we did this work, we did have the stores put their results in a buffer, separate buffer. That's not architecturally visible. And later loads in run-ahead mode can access that buffer and get the value from there, if it's not. Yeah.
So it's not like an approximation there, right? Because if you have some other core, and if I do it right, then
That's right. I think you'll enjoy Lab 7. That's right. We'll get to that when we cover coherence. But yes, this is all an approximation. But the key is, this doesn't need to be correct, right? As long as you capture what you need to capture to do accurate prefetching, it's fine. Right? So the idea is, okay, a pseudo-retired store writes its data and invalid status to a dedicated memory that's not visible architecturally, called the run-ahead cache. It could actually, you could write it to the cache, right? But then mark it as speculative, such that it's not architecturally visible. There are many design choices here. As an architect, you have to make the design choice that makes sense for your processing. But there are many ways of doing it. So when we did it, we put it in a separate cache. We called it cache, but it's really structurally a cache. It's not caching any value. The purpose is the data, communicate data through memory in run-ahead mode. A store pseudo-retires, puts its data there. A load comes in run-ahead mode, gets its data from there. Which means that it's not used in other modes. So you would like to keep this as simple as possible. An independent load reads its data from the run-ahead cache. It doesn't always need to be correct, so it could be very small. Okay. What about branch handling? We discussed this. If you have an invalid branch that cannot be resolved, because by definition, invalid means data is dependent on L2 miss, and that's exactly why you're in run-ahead mode. You don't want to stall for that L2 miss. You don't want to wait for that value. So if you have a mispredicted invalid branch, mispredicted branch that doesn't have its data value yet, well, you're going to stay in the wrong path for the rest of the run-ahead mode. And this is true for any kind of speculative prefetching mechanism. think about that speculative pre-computation thread that we looked at. What if there's a mispredicted branch there, right? That depends on the cache miss. Well, in that case, I guess you'll stall because the cache miss, there's no run ahead in that case. Okay. But if you have a valid branch, you can actually resolve them and initiate recovery in this mode so that you actually figure out the correct path, just like a processor would do, except you're doing it earlier. Okay. Any questions on this so far? So there, what are the advantages of this? I guess I'll give you these and you'll tell me the disadvantages. Because there are just, like everything else, there are advantages and disadvantages. Right? Basically, the biggest advantages, as we've seen with any other speculative pre-execution-based prefetching mechanism, you get very accurate prefetches for data and instructions at all cache levels because you follow the program path. That's true for other prefetching mechanisms also. Right? It's simple to implement. Most of the hardware is already built in. The processor is designed to do processing anyway, and that's what exactly you're doing. Except you need to add a checkpoint, which is a checkpoint of the register file. And in the paper you'll read, actually, that's simplified also. And you need to add these additional mechanisms, control logic, to decide when to exit, when to enter run-ahead mode, and the bits in the register file to keep track of invalid status, and the run-ahead cache to communicate between stores and loads. So, compared to other pre-execution-based prefetching mechanisms, thread-based prefetching that we discussed, it doesn't need to use a separate context. You mentioned that you don't want that context, right? So this doesn't need to use that separate context because it uses the same context as the main thread, except it does it when the main thread is stalled. And there's no need to construct a pre-execution thread also, because you're using the main program. That could have advantages and disadvantages also. Because you're not pruning the program, you're not doing as good as possible you could do. But it's simple. And that simplicity actually is what makes it easy to implement. And some processors, some of them did not see the day of light, but some other processors that have seen the day of light, they employ this mechanism. And some other processors employ it partially to increase the size of, increase the number of misses they can generate in parallel and to reduce execution time. Okay, what are the disadvantages? There must be disadvantages to this also, right?
You know, with flash penalty, I even
That's it. Mm-hmm.
That's
That's right. That's one of the disadvantages. Okay. Well, what else? I think I flashed it for you. If you have a very good photographic memory, you could probably get that. Yes, you have a flash penalty. You have some time where you delay. But maybe you can exit this run ahead early, right? Maybe you could somehow figure out that you're actually not doing too well in run ahead and come back to the main thread. I'm not going to find any misses. And there's a later paper that actually some of these processors actually implement some of those mechanisms too. But I'm not going to go into that right now. What else? Similar to other pre-execution-based mechanisms, there's a disadvantage, right? Exactly. You're executing all of these instructions extra, right? And you're going to execute them again. In a sense, you're doing multiple passes over the program. One for prefetching, and the next one for real. And that increases the activity you have in your program. That increases the energy consumption, if you will, instead of stalling. In a sense, stalling is potentially good for energy. That's not exactly true. But let's say run-ahead execution was useless. Right? Let's say you don't get any benefit from run-ahead execution. If you do this, you execute a bunch of instructions that you wouldn't have executed otherwise. You would have stalled, which means that you consumed a lot of energy. So that's one of the disadvantages. If it's useless, it's energy inefficient. It's useful. If it's useful, if you actually generate another miss and find it and prefetch it, it could actually be energy efficient. because you can reduce the execution time of your program. Yes?
Another disadvantage would
No.
be that if your run-ahead execution window still isn't large enough to handle another miss, then it's useless.
That's right, yeah. So that's one of the reasons for run-ahead being useless. So the benefit, actually, that's a good point. That's kind of a limitation. Your effectiveness is limited by available memory level parallelism, if you will, which means how far ahead are your misses from each other. If your next miss occurs, let's say 5,000 instructions later, then you better execute 5,000 instructions in this run-ahead mode to get to that next miss. But if your next miss occurs 100 instructions later, you just need to execute down 100 instructions to get to that next miss. So that's a limitation. Actually, I'll briefly talk about before we leave how you could potentially address that limitation, that people have proposed. Well, limited by branch prediction accuracy. This is hopefully obvious, right? Because if you have a mispredicted invalid branch, now you're on the wrong path. Now, if you're on the wrong path, it's not necessarily true that you're not prefetching useful data. Because your wrong path might be touching the same data you would be touching on the correct path also. And I'll let you think about that. You've probably written programs that do that. For example, loop iteration, right? If you execute future iterations that will touch data that you're going to touch later on anyway, that's not a problem. And you may have mispredicted the branch. One big limitation is if your cache next miss is dependent on the previous miss. Now you cannot parallelize those two misses. Now that's true for all pre-execution based approaches also, right? If you have dependent cache misses, you cannot parallelize them. You have to have some other method to do that. And your prefetch distance is limited by memory latency. This is similar to what you were getting at. So, so how can you handle this? Well, maybe you add more hardware cost and you do something. What if, let's add one more context here. Let's say you have one core always running ahead of the previous core, of another core, and prefetching data for core 0. So somehow, when this core stalls, this core keeps running ahead and prefetches data for this core. So if you're always on the correct path, you could have two threads, if you will. This thread never stalls, keeps going, and the idea is to speculatively execute the program and prefetch data. This thread stalls, but hopefully stalls are fewer because there's another thread that doesn't stall and prefetch data. Does that make sense? So maybe if you have a speculative core, if you will, and a non-speculative core, this can execute much faster and provide the cache misses earlier to this core, and now this core can execute faster. This is the idea of dual core execution, if you will. And how does this core get ahead? It does run-ahead execution. This is potentially, this way you can eliminate these disadvantages, right? Well, not the dependent cache misses, but now you can prefetch beyond your memory latency. You don't need to stop run-ahead at your memory latency. You could always be in run-ahead mode. Always, perhaps, may not be a good idea, because if you have a mispredicted branch here, you probably want to stop, right? So there are some points you may want to synchronize. So this is not this exactly, but a similar form of this was actually done in Sun Rock. Rock was an in-order processor, so you had two threads. One of the threads was speculative. When the first thread stalled, you would launch this thread, and that would go and speculatively execute the program and feed data to the other thread through the cache, prefetch data for the other thread. And that way you could have two threads, one speculatively executing the program and the other following it. And if you will, both of them go fast. Okay? I guess I'll take your question and we can be done.
Just speculative thread might feel useful work to it.
That's right, exactly.
Can't you avoid doing it again by letting the
Exactly, yeah. So people have proposed those mechanisms also. And actually in some rock, there is some mechanism with the speculative thread. When it does, for example, a multiply or an add, those results are saved, and the non-speculative thread doesn't need to use those results. But the benefits from those is usually not a whole lot, because the cache misses, assuming your program is memory bound, cache misses are what really matter to your performance. But you could save some, you could improve your energy efficiency by not re-executing some instructions. Okay? I think we're done for today. I'll see you next week.